Hello and welcome back to Calculus 1 section 4.5, Linearization and Differentials. So this is a section that does some really cool stuff. You can win some bets with this and so on, right? Go out. But, you know, really low use in purpose now to us because we have computers and calculators and so on. But just 50 years ago, yeah, this is the stuff. So what are we trying to do? We are trying to compute functions, values. And let's paint the picture. You are on a desert island, all the batteries ran out, Wilson is gone, you have nothing to do. So you are trying to figure out how much is square root of 15. Right? And all you have is a very long beach, right, and a stick. And you can actually figure out very precisely the value for square root of 15 or whatever else you want, ln 3, sine of 3 degrees. You can calculate any of that at some point. If I draw a little circle around it, within this circle, y values of the tangent line and y values of the function are very close by. If I draw square root function and I pick some point somewhere and I draw a tangent line and I put the circle around, you see that the y values of the tangent line and y values of the function are very close by. Apparently there is the issue with stream, so this might not be on a video, so take your notes. So what we are gaining here is that y values of the function are close to y values on the tangent line. So why does this work? Well, let's say that the easy value for us to compute in the square root, and it is 16. You can find the tangent line at 16 without any calculators or anything else. And then you can use that tangent line to compute square root of 15 by plugging 15 into the tangent line rather than the square root. And that's the idea. So let me calculate square root of 15 real quick to show what's happening here. So if I want to compute square root of 15, I extract from that information that my function is square root of x, and I want to deal with the tangent line at value 16 because it's easy to take square root of 16. So now I find the tangent line at 16. Slope m for, oh, hold on. We need to find the derivative first. So f prime of x is 1 over 2 root x, if you remember the derivative of root x. If you don't, you just do it on the side as x to the 1/2 and do the n minus 1 thing. So the derivative is 1 over 2 root x. And then we compute the slope when you plug in 16 into this. So we get 1 over 8. Square root of 16 is 4. 4 times 2 is 8. So we have the slope is 8. And then we plug 16 in original function, which is just the square root of 16, to get 4, which gives us 16,4 point. Well, if you have a point and a slope, you can find a line. y equal mx plus b. Y is 4. M is 1 over 8. X is 16 plus b. So that's 4 equals 2 plus b, and b equals to 2. So what's my tangent line? My tangent line at x equals 16 is given, which is close to 15. That's the key. You have to pick a value that it's easy but close to the thing you want to find. So tangent line at this is equal to y equals 1/8x plus 2. And this is the claim now. This is what this is important for, right? Yep. We are going to find square root of 15 is approximated by 1 over 8 times 15 plus 2. You can do this calculation with a stick in a sand. You are dividing 15 by 8, and then you're adding 2 to the whole thing. So how much is 15 divided by 8 if you do it by hand? Okay, 8 into 15. This is the stick in the sand now. We're doing the whole thing with our calculator. 8 into 15 goes once. You put 8. You subtract, you get 7. 70. 15 into 70 goes how many times? Very good. So 4 times, 8. 8 times 8 is 64. We get 6 when you subtract, right? 6 times 8. So that's that. So 8 times 8, 64. So 6, now 60. So you get 7 for 56. Then you get a 4, 0. You get a 4 for 32. No, sorry, 5, you're done. 5, 40, 0. Great. So this is 1.875 plus 2 is 3.875. So my calculation, by finding the tangent line and computing 15 in tangent line, I'm getting that square root of 15 is approximately 3.875 using the tangent line. Now, can anyone punch 15 in the square root of 15 in a calculator? Well, give me next decimal after 5 as well. Square root of 15 is going to be 8729. It keeps going forever. Yeah. Do you see that the first two decimals match? You see how precise this thing was? Remember what I used? Stick in a sand. No calculators, no nothing, right? So this is calculator over here. Of course, right? So you are able to find any value of any square root or ln or whatever, trig function, whatever, as long as you know to find the closest value where you can do it by hand. So now you go and say, okay, sure, but what's the square root of 83? Not a problem. Square root of 83, I'm just going to do the square root of 81, which is 9. So I can do the tangent line for there, for 81, and compute the 83 in a tangent line rather than root, and I'm going to be this close again. Let's do another example, ln 3. So if you're thinking I'm cheating over here with a square root because that's easy, how about ln 3? Which value is close? That is nice and easy to compute. What's close to 3? Well, we can't do ln of 2 either. We need to find a value that is close to 3, but we can easily deal with that with ln. E, beautiful. E. E is 2.7, right? About 2.7. So E. So f of x is going to be ln x, and the value for our tangent line is going to be e this time. Again, zero calculator use. We are going to find very precisely what ln3 is. And you can do this for whatever else you want. So let's go. Where do I start? I start by figuring out the derivative, which is 1 over x. Then I find the slope by plugging in e, and I get 1 over e. So slope is 1 over e. Then I plug e in original function to find y value, and now I have the point e comma 1 as the point, and the slope up there is 1 over e. So now to find my tangent line, I have a y equal mx plus b. Y is 1, m is 1 over e, x is e, plus b. These guys cancel, and we get that b is equal to 0. Right? So b equals to 0 gives me that my tangent line at x equals e is given by y equals 1 over e times x. That's the tangent line. So now if I want to compute ln3, I will say ln3 is approximately the same as 1 over e times 3. Okay, that's easy to compute, because I can approximate this as 3 divided by 2.7. E is about 2.7. Remember, stick in a sand. Multiply by 10, that's 30 over 27. Divide by 3 is 10 over 9. And when you divide this in a sand, you get 1, 1, 1, 1, 1, 1 forever. So ln3 is approximately 1.11 forever if I use the tangent line. What's ln3 in your calculator? 1.0986. Guys, I'm 1 cent off. 1 cent off on a calculation. Go ahead, figure out ln7, ln13, whatever, right? You just have to figure out if your tangent line is close to e squared, e to the 3/2, right? Anything that is easy to compute. So you find the best, closest exponent of e that you can find, and you just compute the tangent line at that point, which, as you can see, can be done without calculator. And then you compute the point that you're the value you're interested in a tangent line, which is linear calculation, rather than in original problem. Just 50 years ago, engineers used to carry the book. The book was called log tables. Now you can go online and buy it as a relic. And it possibly could be the loophole for exams. No calculators. Hey, but I have a book. All right? What is in the book? Answers. ln of 0.01, ln of 0.02, ln of 0.03, ln of 0.04. Every single one of those, right? Eventually ln1, ln2, ln5, ln10, right? That's in the book. Hundreds of pages of that, and sine of 1 degree, sine of 2 degrees, sine of 3 degrees, right? Eventually you hit sine of 30, it says 1/2, right? But that was not interesting, because we know that sine of 30 is, right? What's sine of 31 degrees? Use this, right? So, just 50 years ago, there was no calculators. You couldn't pull the calculator or a cell phone and push ln3 and get the number, right? The only way to do those calculations was this, right? Or to look up in a book, if you have the book of values. So the square root, the ln's, the cube roots, the sine, the trig functions, right? All of that stuff was in that book. And you carry that book around. So if you buy the book and you know, we say no calculator. Go to Rutgers or NGIT, no calculator allowed for anything. So yeah, the rules say no calculator. It's not a calculator, right? And they still kick you out. I taught at NGIT for 2 years. What happened? No, it's just my idea. Which you should generally avoid all of my ideas. Because, yeah, they all have the malicious intent. Alright. So now just statement in red. Linearization is used to approximate values of the function. What I'm going to do now is I'm going to put the entire tangent line procedure in a single formula. Wouldn't that be nice? To take, you see, to take all of what you see on the screen right now, to take all of that procedure and put in a single formula. We can do that. Here it is. L of x is equal to f of a plus f prime of a times x minus a. There it is. So this is the tangent line. This is the tangent line formula for in one line, right? In one formula. So how do you use it? Well, compute the function at a. That's this part over here. Compute derivative at a. That's this part over here. Plug everything into the formula. That's this part over here. So these bubbles that were all separate steps are now all in a single formula. So we're not learning anything new, we're just condensing everything into a single formula. So if I need to compute, let's do square root of 15 real quick. I will say this. A equals 16. That's the cool value that I can deal with, right? And f of x equals root x, right? That's given by what you're trying to do. So now what's L of x? L of x is f computed at a, which is square root of 16, plus the derivative computed at a, which is 1 over 2 root plug in 16. And over here you have x minus 16. In one shot you get everything. So the function is f of x. You want to compute that at a, and a is 16, so plug it in. So L of x is square root of 16 is 4, plus this works out to be 1 over 8. You have x minus 16 over here. L of x is equal to 4 plus 1 over 8x minus 2. And there's your L of x. We had this as a tangent line earlier, but now we got this from the single calculation. And now it's easy to say square root of 15 is approximated by L of 15, which is 1 over 8 times 15 plus 2. And for that we got 2.875, if I remember well. So this is your square root of 15 problem done through the eyes of linearization, which is the tangent line. To be honest with you, since this is dead for us, we have computers and calculators. It's a part of the curriculum, so we do it, right? To honor the ancestors, right? There is poor guys, you know, captains of ships that were doing these things. You're stuck on a ship, right? 2 months, right? Your day is what? You have to eat, execution, and then this. It's nothing else. Like nothing else to do. That's what I said. 3 point. Yeah, please pay attention. It's clearly 3. It's clearly 3 if you look at it. It's 3. Okay? So linearization is developed for us to calculate things in the era when we didn't have the calculator. So what is linearization? Linearization approximates value of the function. Second part of this lecture are differentials. Differentials approximate the change in value of the function. So it's different. So differentials in red. Differentials approximate the change in the value of the function. Now, delta y is y1 minus y2 minus y1. And this is the exact change. But that requires of you to compute the function at x1 and the function at x2 and then subtract those two numbers to get the exact change. In many cases and many situations, it's much faster to compute the differential, which gives you this approximated difference, than to actually compute the values. I know it sounds crazy, but again, you have to think from the angle of no calculator. That's the biggest thing. Right? Of course, you are going to be faster to compute the exact value because your calculator will give you the square root of 4.08, right? But go 50 years back, right? When this was developed much earlier than that, but you know. And again, is this relevant? Right? So let's see what is the differential. Let's derive it. So we start by writing down the pre-calculus notation that y is equal to f of x. And then we differentiate this using Leibniz notation on left-hand side and modified Newton's notation on the right. Newton used to be y, the dot on top, right? That dot changed into a prime. So, you know, when you put f prime or y prime, that's modified Newton's notation. All I need to do is to shift this dx to the other side. So dy is equal to f prime of x times dx. This be your differential. Now, everyone is clear that this f prime is the derivative. What you are not clear yet is that this dx is the same as delta x, which is x2 minus x1. It's x2 that's new minus old, okay? New minus old. And here is the kick. dy is not the same as delta y, but they are close. And that's why we are approximating. So we can say that dy is approximately the same as delta y. So delta y is going to be something that it's pain in the neck to compute without a calculator. So we compute dy, which is close enough, and we can compute it without a calculator. So let me give you an example. Find the change in volume of the cube as its side grows from 3 to 3.06 centimeters. Find the change in volume. Simply, you are asking what's the difference between the old volume when the cube had 3 centimeter side and the new volume now with the 306. You know what happens with the materials when they get heated. They get bigger, right? Making cold, they shrink. Other than ice. But ice actually picks up the moisture and grows that way. It's not the same principle, but anyway. So what do we do? Well, first off, I have the volume for the cube, a cubed. Let's call it x cubed. X cubed. I see that x is equal to 3, and it grows to 3.06 centimeters. That means that my delta x is 3.06 minus 3, 0.06. Remember, new minus old. The first stage of the cube, which is old, is 3, and then it grew to 306. So new, 306, minus old, 3, is 0.06. I need to find the derivative here. So, dv, the volume, is equal to derivative of this puppy, which is 3x squared, times dx, which is actually equal to delta x, so 3x squared delta x. So change in volume is 3 times 3 squared times 0.06. This is 3 times 9 times 6 over 100. So we have 81 times 2. What's 81 times 2? 162. Divided by 100. So the change in volume is approximated by the differential dV, which is 1.62 centimeters cubed. So if the side is to grow, if the side is to grow 0.06, that means all 3 sides, the volume should grow by 1.62. Now, you have the power, right, with your grasp, to check how close this calculation is. So go ahead. Calculate 306 cubed minus 27, right, 3 cubed. So 3.06 cubed minus 27. $1.65, thank you. See? I don't think we're going to make a big deal about 3 cents, right? Because that's the difference, 3 cents. The 3 cube. So new cube minus old cube, right? This is exact calculation we're checking, and we did this without calculating. So you understand that the reason why you don't worry about these things is because you have the calculator to go 306. 50 years ago, 306 times 306, and then when you're done with that, times 306 to get that number minus 27 to compute. Wasn't it much easier here? We didn't take calculator for anything. I was pop, 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 done. So linearization calculates the value of the function, approximates the value of the function. Differentials approximate the change in function. And we approximated now the change in volume as you went. Now, these things are important. Are you guys familiar that the pressure in your tires should be lower over the summer than in the winter? Why? The heat expands, exactly, right? So the change in temperature creates the change in volume, right, which is also change in pressure. There is the formula that connects all of these concepts. So in the summer, when it's hot outside, plus the temperature from the friction between the tire and the road, the only thing that keeps you driving is the friction that is there between the rubber and the road. The tires get hot. With heat, things expand. So, and then the pressure and all of these things. So you want the lower pressure, right? And then in tires, so there is expansion and so on and so on. So then the tires are not exploding. If you don't worry about these things, well, probably you worry about it, changing your tires, exploding your tires. You will find much more debris, the truck tires, over the summer, right, along the highways than in the winter. There's a reason for that, right? So it's the game of this pressure and temperature and everything else. All of that computed with this. What else do we care about? Well, design, right? You have, do you know what the CDs are? It used to be for music, the disc, like plastic disc like this, you put in a CD player. You probably, oh no, you use the Blu-ray, right? So that's the same concept. So there you go. The Blu-ray player, when you put your disc inside the Blu-ray player, the laser which reads the disc is moving linear. This guy has a speed at which it rotates, which is omega, and this one has its speed v, going linear left and right. Great. It shouldn't be difficult for anyone to come up with functions that will read sectors and regions of the disk as it spins. No issue there. You can also find the relationship between these speeds. All of that is a joke physics. What's the major problem of this thing? What's the major problem? What happens when you shine the laser onto a disk? No. What happens when you shine a laser on anything? It heats up. And what happens when you heat up the plastic disc? Exactly. So you have to have temperature probes, and you have to have a whole spiel of other electronics in there designed so that your whatever you are, it's not like that. Because it will be like that because the speeds will not be matching. Right? So that's that technology. Where do you calculate that? Right here. Is anyone taking the train? Ever? And then what happens during the winter? Tak 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 tak, right? And in the summer, tak tak tak. Barely hear anything. Why? The gaps in a rail. Why do we have a gap in a rail that it's, I don't know how many expansion of the track? In the summer, it's hot. It expands linearly. It can't go left and right. It better not, right? Because you need the parallel tracks. The only way it can expand is this way. If you don't leave those gaps to be filled in over the summer, then if you set them up this way, when they start expanding, they pop out. Go and look at the early railroad design, and people didn't know this stuff, that it's relevant on that length. You see the tracks mangled by. It was just a little bit of the sun, right? You have to design and do that. Elon Musk is doing what? Thinking about Hyperloop. Does anyone know what the Hyperloop is? Go look it up. Imagine that engineering that has to go into that one to make a train that goes faster than the airplane, much faster than the airplane, on a cushion of air, in a tube. How do you design a vacuum-sealed tube where you also have to worry about linear expansion of the tube, unless you're going to bury everything underground? We have a problem with earthquakes then. Don't put it in California, right? So, you want to be engineers? There you go, right? Because this solves the real problems that you have to face, right? You have to sit and you have to design things so they fit. Otherwise, it's not going to work. Bridges. You ever wondered why you have those gaps, right? That you drive over on a bridge? You go over a horizontal bridge, like gap. You can probably wedge your foot in the winter. In the summer, bridge expands, right? It connects like that. And in the winter, bridge contracts, so you still have space. You still drive over it, it's not a problem. It's going to be that much of a gap, but you need to design those things. Bridges, railroads, the Blu-ray stuff, and so on. So yeah, so you see where your money is when your stuff is. We are going to take 2 minutes break and have a very short section after this on mean value theorem. It's a 15-minute thing, so we're good. See you all in 2 minutes.